Welcome to the Arithmetic Zone, and here we have another bonus tutorial, and again we're going to do it on an AP Physics C mechanics topic. Topic of our day will be the 1993 FRQ number 2. So let's read the question first. A car of mass m, initially at rest at time t equals 0, is driven to the right as shown above along a straight horizontal road with the engine causing a constant force F sub naught to be applied. While moving, the car encounters a resistance force equal to negative kV, where v is the velocity of the car and k is a positive constant. So the first question, the dot below represents the center of the mass of the car. On the figure, draw and label vectors to represent all the forces acting on the car as it moves with the velocity v to the right. So first question is pretty simple. All we do is make a free body diagram of the car. So we know this car is on the ground, and we only have horizontal forces, so let's just get the vertical ones out of the way. There's going to be a normal force. We'll call it Fn. And there's going to be Fg, which I'm going to label as Mg. Now we got to see the horizontal forces. So the question explicitly says there's a constant force, F sub naught, and v is to the right, so F sub naught is going to be right here. And then there's a resistance force, negative kV, and this force resists the force of F sub naught, so I'm going to write over here kV. Now, why did I not write the negative sign? Well, the fact that the problem calls it a resistance force and then they include the negative sign, that implies that it's going to be in the opposite direction of F sub naught. So all we have to do in our free body diagram is to have kV going the other way, and we don't have to include the negative sign because that's the question telling us it's going to go in the opposite way. The next part, we got to determine the horizontal acceleration of the car in terms of k, v, F sub naught, and m. So it's pretty clear the horizontal forces in this problem are unbalanced, while the vertical forces F, Fn, and Mg will be balanced. So when finding the acceleration, we're going to use the Fnet formula, where Fnet is equal to ma. And we're only going to care about the horizontal forces. So Fnet is going to be F sub naught minus kV, because that's the summation of the horizontal forces. And then we're going to set that equal to ma. Now all we do is simply divide m both sides to get our answer of F sub naught minus kV all over m equal to the acceleration. This is a pretty simple part, but unfortunately that's going to be the easiest this question will get. For part C, we have to derive the equation expressing the velocity of the car as a function of time t in terms of k, F sub naught, and n. So you might be thinking, oh, you just take the A expression we found in the last part and solve for v, right? Well, no. We got to make sure it's a function of time, and our acceleration expression did not feature time anywhere. So what we're going to have to do is we're still going to use the acceleration equation. So let me just rewrite it first. A equals F sub naught minus kV all over m. But what is acceleration specifically? Well, it's the instantaneous rate of change of velocity. So it's dv over dt equals F sub naught minus kV over m. And now, you may guess, we have to use separation of variables in order to get an expression v as a function of time. So we're gonna have to make it so that all the v's are on one side while the dt is on the other side. So let's first deal with that m. So if you multiply by m on both sides, you'll get m dv over dt equals f sub naught minus kv. Now I want to multiply dt by both sides. So mdv is equal to f sub naught minus kv, all of that times dt. And then finally, we can divide f sub naught minus kv on both sides and have mdv over f sub naught minus kv equals dt. So you might be thinking, well, I got the v's on the same side, I got the dt on the other side. How on earth am I supposed to integrate this whole expression? Because usually when you have to integrate expressions like these in AP Physics, it's usually just a simple dv over v. But no, this is mdv over f sub naught minus kv. If you're having trouble imagining how to integrate this, well, you got to remember which values are constants. M is mass, that's a constant. F sub naught, the question told us it was constant, so that's also a constant. And K was explicitly stated to be a positive constant. So while this isn't what the expression is at all, just imagine that this left integral, imagine it's just the integral of, say, 3 dx over 2 minus 5x. And then suddenly you see, oh, this is just going to result in an ln and a u sub. So let me just go get rid of that. And we're going to use u substitution on this. So remember, the variable in interest here is v, not x. So u, we're going to make the bottom part of the fraction, f sub naught minus kv. And then the derivative of u, f sub naught's a constant, so that's 0. V is a variable that isn't constant, so we got to use power rule here, and we're left with negative k times dv. But there is no negative k in our expression, but there is an m, so we have to balance our du expression right here so that it results in just this m. And all we really have to do is just get rid of this negative k. So if we multiply this by negative 1 over k, that should cancel out the negative k, and we're just going to be left with m. So let me just draw an arrow right here, and I'm going to move the m outside just to make it a little more clear. So it's m times negative 1 over k, so negative m over k, and then the integral of du over u, and then all of that is equal to the integral of dt. So now what we're going to do is we're going to integrate this whole equation. So negative m over k times ln of u, ln of absolute value of u, I should say, and this is equal to, this is just going to be t. Now usually when you solve problems like this, you would have definite integrals from v to v sub naught and then t to 0 from top to bottom. But I'm using indefinite integrals. I just personally think that this method makes more sense, especially if you take calculus. So because we're using indefinite integrals, we have to account for the possibility of a constant. So I'm going to write plus c. C is going to be a constant of integration. We're going to obviously have to address that later on. So we can't just leave it there. But in any case, what we should now do is substitute u back for what it originally was. So negative m over k ln of absolute value of f sub naught minus kv equals t plus c. Now, before we solve for the constant of integration, what I'd want to do first is get this expression so that it's solving for v. So we're gonna, on both sides, we're going to multiply, in order to get rid of negative m over k, we got to multiply by negative k over m. So have another arrow, and it's going to be ln, the absolute value of f sub naught minus kv equals negative k times t plus c over m. Now, if you try to multiply a constant to the constant of integration, it's still going to be c. It's not going to change. So this is just going to be, and likewise if you divide by m, same thing. So it's going to be, it's going to result in negative kt over m plus c. Now this is getting a little messy, so I'm going to clear this, and then I'm going to rewrite it so we have it right here. So what do we do next? How are we going to isolate the v? We got to get rid of the logarithmic, the natural log. So we have to exponentiate this using Euler's numbers. So if I have e like exponentiated to this whole expression and e exponentiated to this whole function, the e and the ln will cancel each other out. And then I have f sub naught minus kv equals, and now this is where the trippy math comes in. So if I exponentiate an expression like that, and then it's separated with like a plus right here, then I can separate it into two terms with the same base exponentiated between each of the terms. So what is this going to look like? It's going to look like e negative kt over m times e to the power of c. And as I said before, when you manipulate the constant of integration with another constant, which Euler's number is a constant, the result is still going to be the constant of integration. So e to the power of c is just c. So really, this just results in f sub naught minus kv equals ce negative kt over m. So after that, suddenly it becomes much simpler to find v. Subtract both sides by f sub naught to get negative kv is equal to ce negative kt over m minus f sub naught, and divide both sides by negative k, and then we get that v is equal to ce negative kt over m. Remember, if you divide c by negative k, it's still gonna, the coefficient's still just gonna be c. It won't even be negative c, it'll still just be positive c. And then f sub naught, negative f sub naught over negative k is just gonna be positive f sub naught over k. So we finally got an expression that solves for velocity, and it is a function of time, but we have a constant of integration, and we need to have at least one known value of velocity in order to get rid of it and find a definite value. So if you go back to what the question originally said, it said that the car starts at rest at time t equals 0, and when something's at rest, velocity is equal to 0. And they said that time was equal to 0, so negative k times 0, that is supposed to be a 0. I apologize for how that looks. Plus f sub naught over k. Now, this is just e to the 0. Anything to the power of 0 is 1. So 0 equals c plus f sub naught over k, which means c is equal to negative f sub naught over k. This is a constant. It's the division of two constants. So we're going to go back to our expression and we're going to finalize it. And now that we know c, we can finally just plug it back into our v expression we found earlier, and we get our final answer of v equals negative f sub naught over k times e equals negative kt over m plus f sub naught over k. You could leave it off right here, but I'm going to take the extra step and I'm just going to factor out the f sub naught over k because it is in both terms, and inside will just be 1 minus e to the power of negative kt over m. So we finally got our velocity function of time. Man, that was a lot of work. But that was only part C. Still have 3 more parts to go, but thankfully the worst part of the question is over. So now we got to derive an expression for the acceleration of the car as a function of time in terms of the same variables as before. Now, we just found the velocity function of time. So thankfully all we have to do is just find its derivative. So I'm going to actually rewrite the v expression how it was before I factored it, because it will be easier to find a derivative from that step than it is when it's factored. So just bear with me for a minute. Alright, so acceleration as a function of time is just a derivative of the velocity function of time. So we're going to have to write out that a is equal to d dt of the velocity function of time. So d dt of that whole expression. And then now we're just going to use our derivative rules in order to figure this out. So we know that negative f sub naught over k is just a constant. And then our variable in interest here is t, because t is not a constant. So e to the power of anything, the derivative is just e to the power of that same value times the derivative of what's in the exponent. So negative f sub naught over k times e to the power of negative kt over m times the derivative of negative kt over m, which is just negative k over m, and then f sub naught over k is a constant. So the derivative of that is just 0. So in the end, our acceleration function, if we multiply this coefficient with this value right here, the result is a is equal to f sub naught over m times e negative to the power of negative kt over m, because if we look at this closely, we can see that the k's cancel out, the negatives cancel out, we're just left with f sub naught over m. So that was much easier to figure out. Now we have to sketch a graph of the car's velocity v as a function of time while labeling important values on the vertical axis. So we did this already in part C. We found velocity as a function of time. So if you're having trouble imagining how that function looked, which I'm going to rewrite it again, it was v is equal to negative f sub naught over k times e negative kt over m plus f sub naught over k. If you don't know how that looks, well, we have an e, specifically negative e to the power of the negative variable. If you don't know how that graph looks, it is going to be concave down. And the problem in the beginning explicitly told us that this car starts at rest, so we know it's going to start at v equals 0. So let me just label this as v and this is t. So we know it's going to start at 0 and we know it's concave down. So our curve is going to look like this. And we know that acceleration is going to eventually, or at the very least, approach 0 because there is a resistance force that's getting larger as the velocity increases. So we did most of the question already, but we have to label important values in the vertical axis. So the important value in question is when acceleration is approaching 0, which is about right here. So we need to find what the acceleration is at that point. And so it's basically 0. And if you think we have to use any of these, the velocity function at time or even the acceleration function at time, don't worry. We actually can just use the acceleration function we found in part B, like much earlier, where a is just equal to f sub naught minus kv over m. We know that at this point, a is about 0, so we're going to set this whole expression to 0. We can multiply by m both sides. We'll still get 0 is equal to f sub naught minus kv. And then now we're just going to solve for v, so f sub naught is equal to kv if you add kv on both sides. And v is just going to be equal to f sub naught over k. That is what v is equal to when acceleration is 0. So we're going to label right here f sub naught over k. And that's all we have to do to label this and get full credit for that question. This time we're going to sketch the graph of the car's acceleration. A is a function of time t. So very similar to the last question, except now we're going to do the acceleration function. So again, I'm going to write it if you don't know how that graph is going to look. We found that a was equal to positive f sub naught over m times e to the power of negative kt over m. So this is a positive e to the power of a negative variable, which that is a concave up graph. And we know that acceleration should approach 0. So we're going to have it start right here and have it approach 0 like that. So note this little ellipse should not be there, but it is a concave up graph. And again, I'm going to label the axes A and T. If you don't know how these graphs are supposed to look, you can substitute in constant values for f sub naught, m, and k. They should all be positive. Make sure you have them all as positive, but you can substitute in values for them and then just graph it on your calculator to see what the shape looks like. Now, don't use that strategy to see where it begins. You have to use the problem. So like previously we said that the problem told us the car starts at rest, so we knew that that graph had to start at 0. Just use the graphing strategy on your calculator to know what the shape of the curve should be and not necessarily where the curve is located. So again, we know that acceleration is supposed to approach 0, and we got to label important values on the vertical axes. So this isn't very important. I mean, acceleration is just 0, but I think that starting acceleration is important. So what's true at the beginning of the problem when time is equal to 0? Velocity is equal to 0. So we can use that same expression from part B, where a is equal to f sub naught minus kv over m, and we can substitute in v for 0, which if we substitute in v 0 for v, then a is just going to be equal to f sub naught over m, which is its initial acceleration and also happens to be the maximum acceleration. So there you have it. We've gone through all the parts of this one free response question, which was very heavily calculus based. And if you're in this class and you struggled on the math portion for this question, then you shouldn't worry too much, because this is pretty much the hardest it'll ever be and the hardest you'll most likely ever see questions on. I wanted to go over this question because it was heavily calculus based, which is my specialty, and I wanted to show you alternative ways to integrate that expression in part C instead of what College Board usually recommends. Anyway, I'll see you guys later for more computer science and math tutorials in the future.